Hello again, Chem 2 students. This is Mr. Keister, and today's video is for Friday, October 2nd, 2020, which I believe is our scheduled 31st day of school for the fall semester. Always keep in mind, though, that the dates could change for a variety of reasons, but the lessons and the order that those lessons are presented will always remain the same regardless. So let's take a look at the do nows, our schedule for today. So no papers to pick up today. We're going to continue on. As I said yesterday, this is a two-part lesson. We're going to continue with that today over the Bohr model. So your homework for today was to complete numbers 1, 2, and 3, and number 9 on the Bohr model assignment. Hang on to that. We're going to finish it today. Of course, the answers to those are particular problems are already posted on the backboard and also in Canvas on my answer keys page. So you're certainly welcome to check your answers if you want to. They were posted by 7 a.m. this morning. Today we'll finish up with the first portion of Unit 3 by summarizing both particle and wave theory of light, which we talked about yesterday, which came about from the work of Planck and Einstein, which then led to, or leads us to, the Bohr model of the atom. So you should be able to finish the assignment. That will be due Monday. I am collecting it for a grade. Reminder, I have posted some videos in Canvas that might help you in your understanding of the theory. They're Professor Day videos. We watched one yesterday. We're going to watch another one today. Those are available to you in Canvas. I encourage you to watch them again if you need to in order to reiterate or review what we have talked about this past 2 days. All right. Again, this is leading us to the modern atomic theory. It's a bit more advanced than the plum pudding model of the atom from J.J. Thomson, and of course then the Rutherford model of the atom, which followed that. We're getting way beyond that. So if you need to review and go back over what we've already talked about, by all means, please do that, because this is crucial into what's coming next, which is the modern atomic model, which is the quantum mechanical model of the atom. We're getting to that very soon. So, having said that, let's pull up today's notes. And there we go. So, the Bohr model, there we go. The Bohr model of the atom. So, the work of Planck and Einstein led the way for understanding how electrons are arranged in atoms. All right. So, now we're going to link electrons with light and EMR. All right. In 1913, Niels Bohr, so this is just a few years after the work of Planck and Einstein, Niels Bohr offered a theoretical explanation for line spectra. Okay, each element gives off a line emission spectrum. All right, basically bands of light based on the electron arrangement in the electron cloud of its electrons for each atom. This was not known hardly at all by J.J. Thomson and Rutherford. We knew that electrons were not in the nucleus. We knew they orbited the nucleus and that they were negatively charged. They orbited somehow out there in the electron cloud, but that was about the extent of it. This is where that changes dramatically. All right. A particular source of EMR, radiant energy, may emit a single wavelength. This is called monochromatic radiation, such as a laser, a red laser. Only emits red light. All right. Most sources of radiation, like an incandescent light bulb, a star like our own sun, etc., produce radiation containing many different wavelengths. Of course, you know that our sun produces white light, which when broken down by a prism yields all 6 or 7 colors of the visible spectrum. You know, violet all the way up to red. 6 or 7, meaning 7 if you subscribe to the theory that indigo is its own color. It is, it isn't, who knows, who cares? All right, it's there. Not all radiation sources produce a continuous spectrum. When different gases are placed under reduced pressure in a tube and high voltage is applied, you're going to see this in our lab on Monday, the gases emit different colors of light, different bands, all right? When light coming from such tubes is passed through a prism, only lines of a few wavelengths are present. So For instance, a sodium vapor lamp, like we talked about the other day in a parking lot, emits yellow light, all right? But when you look at that yellow light through a prism, you're going to see that it's composed of various other individual colored bands of light that when merged together produce that yellow light that we see. This is what a prism allows us to see that our eyes cannot do, all right? And again, we're going to see that in Lab Monday. These lines are separated by black regions, which correspond to wavelengths that are absent in that particular light. So remember, we have violet, blue, yellow, orange, violet, blue, green, yellow, orange, red, and indigo's in there somewhere. All right. So if yellow light that we see from a parking lot light only gives off, let's say, 3 bands of light, those 3, then all this in between is dark. All right, all this in between is dark. And so that's what he's talking about in a line emission spectrum. Okay. Now, a spectrum containing radiation of only specific wavelengths is called a line spectrum or a line emission spectrum. All right. Again, you're going to get to see these for yourself on Monday in our labs. Let's go on to the next page. So Niels Bohr took Rutherford's model of the atom, where electrons orbit the nucleus. That's about all we knew then. And Planck's idea that energies are quantized had proposed that only orbits of certain radii corresponding to certain energies out in the electron cloud are permitted. An electron is in a permitted orbit, has a specific energy, all right, and is said to be in an allowed energy state. Bohr called these energy states energy levels. You've probably heard that in Chem 1 or another class. This is where the term energy level came from. Niels Bohr, all right? An electron in a permitted orbit has a specific energy and is said to be in an allowed energy state or energy level. Using this assumption, Bohr showed that the electron could circle the nucleus only in orbits of certain specific radii, all right? Basically, this is the nucleus, and then this is the electron cloud. We now have varying orbits that are a certain radius from the nucleus, all right? And each of those orbits corresponds to a specific amount of energy, all right? A specific amount of energy. And so based on that, we are going to go to Professor Dave and have him talk about it, and then we'll come back and do some calculations, all right? So let's roll with Professor Dave, and I'll be back soon, okay? Take it away, Dave. Oh, let me erase our little model of the atom here. Don't want to block Dave's view, or our view of him. All right, here we go.
Professor Dave here. Let's talk about the Bohr model of the atom. He knows a lot of science stuff, Professor Dave explains. Once Einstein extended Planck's idea of energy quantization to electromagnetic radiation, other physicists made some similar strides. Niels Bohr was dealing with some problems that were arising with the structure of the atom. If an atom has positively charged protons and negatively charged electrons, why are atoms stable? Why don't the electrons just collide with the nucleus? What were these emission spectra that we can see? What is it about different elements?
That's what I was talking about, an emission spectrum.
Bohr answered these questions with his model of the hydrogen atom. He extended the idea of energy quantization and said that the potential energy of the electron in a hydrogen atom is also quantized. This means that an electron can't have any imaginable energy, but can only inhabit certain energy levels that are at fixed distances from the nucleus. Each type of atom has its energy levels at different values due to its unique number of protons in the nucleus. And an electron will transition from one energy level to another when a photon of a very specific energy is either absorbed or emitted by the electron. The energy of the photon will correspond to the difference between the two energy levels. So if the electron in a hydrogen atom goes from the n equals 3 to the n equals 2 energy level, a photon will be emitted that is equivalent to that specific energy gap. Another transition has a different energy gap associated with it, and therefore generates a photon of that particular energy. And to go from lower to higher energy levels, an electron must absorb a photon of that particular energy. For a hydrogen atom, the energy levels depend on the Rydberg constant and are given by the following equation. We typically just measure the change in energy of an electron during a transition, so we can modify this equation to include the change in the energy level.
We'll get to that shortly.
Where the electron ends, and n initial is where it begins. Using this equation, we can predict the wavelength of photon associated with any possible transition for the hydrogen atom. Take this transition, for example, from 4 to 2. Plug in where the electron starts and where it ends, and we get the change in energy of the electron, which equals the energy of the photon. From energy, we can get frequency, and from frequency, we can get wavelength. We group the transitions according to the energy level they land on. All the ones that end on n equals 1 are called the Lyman series. The ones that end at n equals 2 are the Balmer series, and so forth. Notice that the energy level gaps decrease as n increases, and n equals infinity is actually a finite distance from the nucleus. If an electron goes beyond that, it is considered to have been ejected from the atom. The Balmer series happens to contain transitions that generate photons of visible light. These are the ones found on hydrogen's emission spectrum. These lines correspond to the electron's transitions that end at n equals 2, and the resulting photon that transition emits, which just happens to fall in the visible spectrum. As we said, these energies are unique to hydrogen. Every element will have its own emission spectrum because every element has a unique nucleus and therefore differently spaced energy levels. In this way, an element's emission spectrum is sort of like a fingerprint unique to that element. This is how we can know the composition of objects in space, by analyzing the light we see. Let's check comprehension.
All right. Good to go. Thank you again, Professor Dave. All right. So, let's talk about what Dave was telling us there. So, using this assumption then that Bohr showed that the electron could circle the nucleus only in orbits of certain specific radii, and the allowed orbits have specific energies are given by this equation. All right, this is called the Bohr-Rydberg equation. All right, whereby E is the energy of an electron in a specific energy state, which we call an energy level. All right, in a particular energy level, we call that N. All right, that's why the subscript N there. RH is the Rydberg constant. All right, 2.18 times 10 to the minus 18th joules. We give this a negative value so that our energies come out positive. And 1 over n squared. N, of course, being the energy level. So, as we go, as I kind of drew a little bit ago, I drew a little in a circular way. So the nucleus is here in the center. So this is the nucleus. The first energy level is going around the nucleus like so. The second one, the third one, that isn't centered very well, but you get the idea. And so on and so on. So each orbit corresponds to a different value of n, and the radius of the orbit gets larger as n increases. Actually, it's a function of n squared. Hence n squared in the equation. In the lowest energy state, n equals 1, the radius of the electron's orbit is around 5.29 nanometers. The radius of the next allowed orbit, n equals 2, is 4 times that amount since it's a function of n squared. All right. Now, for an energy transition, then, if you're going from one energy level to another, then as Professor Dave said, the electron either has to absorb a certain quantity of energy based on the photon or the radiation, or it has to emit energy. So in order to go from a lower energy level to a higher, it's got to absorb more energy. To go from a higher energy level to a lower, it's going to give off that energy and then drop down to a lower level. Okay? So this is a modified equation based on the Bohr-Rydberg equation, whereby we can calculate the change in energy as an electron transitions from one energy state or one energy level to another. So let's do an example of that right here. So let's say if an electron goes from n equals 1 to n equals 2. So the first energy level to the second. So our first energy level is the initial one. Our second energy level then would be the final one. All right, so here's our equation right here. So this is energy transition, meaning changes energy levels. Make sure you knew that. All right, so delta E then would be the negative Rydberg constant, 2.18 times 10 to the 18th, I believe it is. Negative 18, sorry about that. Times 1 over our final energy squared. Our final energy level is 2, so that would be 2 squared, minus 1 over, our initial energy level is n equals 1, so that would be 1 squared. 1 over 1 squared. All right, so 1 over 2 squared is 1/4, that's 0.25. 1 over 1 squared, of course, is 1, so 0.25 minus 1 is negative 0.75. So when we take negative 0.75 times the Rydberg constant, of course, this is negative, it's going to give us a positive answer, all right? So delta E to 3 sig figs, which is all we got to work with here, is 1.64 times 10 to the negative 18th joules, all right? And it comes out positive, all right? If delta E is positive, that means energy is absorbed, all right? And that's what must happen to go from a lower to a higher energy level or energy state. And then likewise, if delta E comes out negative, then energy is released or emitted, all right? Which is what happens when you go from a higher to a lower energy level. Just as Professor Dave explained in his video, all right? So let's go on to the next page. This is the Bohr-Rydberg equation, all right? The energies are negative for all values of n. The lower the value of energy, the more stable the atom will be. In other words, the most negative it will be. And for n equals 1, this is called the ground state of the atom. If an electron is in a higher energy state or energy level, we say it is in an excited state. Bohr assumed that the electron could jump from one allowed energy state to a higher one by absorbing photons of radiant energy of a specific frequency, and conversely, that energy is emitted when the electron drops to a lower energy state. All right, this was proven. How do we know all this? How did Bohr know this? How can we verify that? This was proven by Bohr's line emission spectrum of hydrogen. All right. How many electrons does hydrogen have? Its atomic number is 1, right? So 1 electron. So you're thinking, okay, if there's 1 electron, then it's just orbiting around the nucleus in some particular random way. Well, no, it's not a particular random way. And his line emission spectrum proved this. When he did the line emission spectrum of hydrogen, he came up with 4 bands of light. You'll see it in lab Monday, all right? So hydrogen produced 4 bands of light. 4, not 1, 4, all right? And those bands of light all had different wavelengths. Different colors, which then means they had different frequencies, which then means they had different energies. All right, different energies. So if they had different energies, they had to be in a different energy state or different energy level. This was his proof that the electron cloud was just not some random area out there where electrons are orbiting, but that it was composed of specific energy levels. All right. This was a crucial and amazing discovery, which took us to a whole nother level of the atomic model. All right. This was big, big, big. All right. The frequency of this energy corresponds exactly to the energy difference between the initial and final energy levels. So the change in energy, this was on Dave's video too. The final energy minus the initial energy then corresponds to Planck's equation, the energy associated with a quantum or photon flight. And by substitution, one can find the relationship then between the frequency of the absorbed or emitted light and the principal quantum number or the energy level of the 2 energy states. So we're going to substitute in Planck's equation into the Bohr-Rydberg equation. All right, so we're going to combine. And again, this was shown on the video there towards the end. Combine the Bohr-Rydberg equation and substitute in Planck's equation, and we get this right here. This is a derived equation between the two that is done simply by substitution. So the frequency of the light emitted in a line emission spectrum is equal to the Rydberg constant over Planck's constant times 1 over nf squared minus 1 over ni squared. Where ni and nf, again, are the energy levels, which we're going to find are called the principal quantum number in the quantum mechanical model of the initial and final states of the atom. A positive value for frequency means that the energy was absorbed. A negative value for frequency means that the energy was emitted. Again, frequency is not negative, all right? Just like energy is not negative. It's just telling us in which direction it went, and that is released or out if it's negative, positive if it's coming in, okay, or gaining in energy. So the positive and negative signs are just telling us which direction the energy was going. All right, was it coming in? Was it going out? Okay, so let's do an example using this combined equation between Bohr, Rydberg, and Planck. So this asks us to calculate wavelength of light that corresponds to the transition of the electron from n equals 4, so that's our initial energy level, to n equals 2, which is our final energy level. Is the light absorbed or emitted? We should be able to answer that, without even doing the math. All right. If you're going from a higher energy state to a lower energy state, you got to get rid of energy. All right. You got to get rid of it. So the light then, of course, is emitted, which means we're probably going to get a negative answer for frequency, but of course we just know that that means it's emitted. So we'll remind ourselves of that here in a minute. So we're going to use our derived equation here, the Bohr, Rydberg, and Planck equation combined, where frequency is equal to negative Rydberg constant over Planck's constant, all right, times 1 over nf squared minus 1 over ni squared. All right, so our frequency then is equal to negative 6.28, or sorry, negative 2.18, sorry about that, times 10 to the minus 18 over Planck's constant, 6.63 times 10 to the minus 34. So a little interesting side note here. We have a constant divided by a constant. Well, if those two constants are always the same, which they are, then when you divide one by the other, it's going to give yet another constant. All right? And I'll show you that in a second. So then this is 1 over our final state is n equals 2, 1 over 2 squared, minus 1 over initial is n equal 4, 1 over 4 squared. So Rydberg's constant divided by Planck's gives us another constant, all right? And someone in years gone by said, well, why don't we just name that for the guy who explained that for us? It comes out to be negative 3.29 times 10 to the 15th. Keep it at 3 sig figs there. And like I said, some bright student way back when said, well, let's just name that for the guy that explained this to us. And they called it Keister's constant. I don't take any credit for that. And it's not certainly published in any chemistry journal or textbook. So we'll just kind of keep that to ourselves, okay? And then, of course, 1 over 2 squared is 1/4, 0.25. And 1 over 4 squared is 1/16, which is 0.0625. And 0.25 minus 0.0625 is 0.1875. Multiply that by that aptly named constant over there, and then the 3 sig figs. Our answer comes out to be negative 6.17 times 10 to the 14th hertz. Keeping in mind, frequency is not negative, all right? This is just confirmation that our light was emitted, all right, where it's negative because it was released, which then means that it's 6.17 times 10 to the 14th hertz released, or emitted, I guess we're using that terminology here. Okay? And so there is our answer there to 3 sig figs, which is all we got to work with, okay, from our constants. So now we have our frequency. It asks for wavelength. All right, so now we use the speed of light equation. C is 3.00 times 10 to the 8th. We have our frequency 6.17 times 10 to the 14th, and times the wavelength. So we'll divide out the frequency. And our wavelength to 3 sig figs comes out to be 4.86 times 10 to the negative 7 meters. And again, if we convert that, which is fine, that's a good answer, but let's take it a little further. Remember, our visible spectrum is lined up in nanometers. So let's just do a quick little conversion here, times 1 billion nanometers over a meter, all right, where the meters cancel, and that gives us 486 nanometers, all right? So think about where that is on the visible spectrum. Remember, violet's down in 400. Well, let's just get it here. I just so happen to have it right here. So here's 400. Green is at 500. So 4 where are we at? 486 is kind of right in here somewhere. I would say that's probably bluish green, more blue than green, maybe more green than blue. But let's call it blue-green light. So the energy transition of this electron from n equals 4 to n equals 2 is going to give off light in the blue-green region. Okay? Okay, last thing for today. The wave behavior of matter. So Bohr, Einstein, and Planck all contributed to the particle theory of light. All right? Is that they characterize radiant energy in terms of photons and quantum. Okay? Depending on experimental circumstances, though, radiant energy, of course, also appears to have wave-like characteristics. We talked about that early in the unit. A Frenchman, Louis de Broglie, looks like de Broglie, but it's French, and I don't take French, but I'm pretty sure that's how you pronounce it. Louis de Broglie developed a hypothesis that explained this phenomenon. How could you have things acting like waves and things acting like particles at the same time? This is where wave-particle duality, that term, comes from. He proposed that the electron orbiting the nucleus could be thought of as a wave with a particular wavelength. All right, so now the electron itself, even though remember, photons have no mass. Now, electrons have very little mass, remember, but they do have a little. But yet, de Broglie is proposing that an electron can also behave just like a photon does. All right, in other words, that it has a wavelength associated with it. He added that the wavelength of this electron or of any other particle depended on two things: its mass and its velocity. And this is the de Broglie. Whoops, better erase that there. This is the de Broglie equation, all right? And this wavelength here is named for him. It's called the de Broglie wavelength. Of course, it's like any other wavelength that's measured in meters, all right? This, of course, is Planck's constant. We know what that is. 6.63 times 10 to the minus 34 joule seconds. This is our mass now in kilograms. So this is the SI unit of mass, which must be used here for proper unit analysis. This is in kilograms. This is our velocity or speed in meters per second. Because de Broglie's hypothesis is applicable to all matter, not just photons, but to electrons and so forth, any object of mass m and velocity v would give rise to a characteristic wave. However, an object with any significant mass, even a golf ball, would give a wavelength so small that we could not detect it. But when you have a very small mass, such as that of an electron, that now all of a sudden that wavelength is possible to be seen. It's actually observable. And this is how his equation and his theory was proven. All right. For an electron, though, it's an observable wavelength is possible because its mass is so small. So let's look at that. So what would the de Broglie wavelength be? So we're looking at the wavelength of an electron. If its mass is 9.11 times 10 to the minus 31 kilograms. Again, the unit for the de Broglie equation for mass is kilograms, so that's fine. And it's traveling close. Well, actually, electrons do travel very close to the speed of light at 3 times 10 to the minus, or times 10 to the 8th meters per second. All right, so this is the de Broglie equation. Wavelength equals Planck's constant over n times v, 6.63 times 10 to the minus 34 over 9.11 times 10 to the minus 31 times 3.00 times 10 to the 8th. All right, and in doing that, we get a wavelength of 2.43 times 10 to the minus 12 meters, which is 2.43 picometers, which is observable, all right? Observable. Within a few years after de Broglie published his theory, the wave properties of the electron were proven experimentally by diffraction, the same method used by an electron microscope. Here is where that wavelength was observed, which then proved his theory. So, wave-particle duality is where we are at even today with not only electromagnetic radiation, but also matter. Okay? So, whoa, that's a lot to take in this last 2 days. I understand that. If you need to, and I encourage you to, go back over the notes for the last couple of days. Go back over go back over Professor Dave's videos and try and absorb all this information. Because, like I said, this absolutely revolutionized the atomic model. All right, taking us from J.J. Thomson and Rutherford to the modern atomic theory, which is the quantum mechanical model of the atom, which we will be getting started on very soon. So, your assignment is to finish the assignment we began yesterday. That is due Monday. I'll be collecting it then, and then we're going to head back to the lab and look at what we have just studied the last 2 days and look and see what that tells us back there in real time, in real life. So, until then, this is Mr. Keister signing off. Take care, everyone. Stay safe. As I said yesterday, now more than ever, stay focused and work hard. Take care, everyone. Catch you next time. See ya.